Hello, my name is Angelica Owens, and this is me and Caden Livingston's Water Tower Project presentation. To start off, I'm going to be talking about the importance of access to clean drinking water. Access to clean water is a fundamental human right that we as Americans take for granted, yet millions of people worldwide lack this necessity. Sub-Saharan Africa is a region that faces significant challenges in providing safe and reliable water sources for its population. Without having access to clean drinking water, this region, like many others, faces famine, diseases, and in worst cases, death. As Christian engineers, it is our job to provide a solution that will improve the lives of people in this region. Our mission is to design and implement a sustainable and efficient trust water tower that provides clean drinking water in rural Ethiopian communities, thereby enhancing their quality of life while promoting socioeconomic sustainability. Our vision is to transform lives in rural Ethiopia by implementing reliable water infrastructure solutions, thereby reducing the daily burden of water scarcity among the community. By utilizing innovative engineering and strategic partnerships, we will create a future where every person will have easy access to clean and safe drinking water. When starting our research, we found that Ethiopia is one of the most affected countries by water scarcity in sub-Saharan Africa. As of 2020, only 49% of Ethiopians had access to at least basic drinking water services. We selected the village of Taruba in Ethiopia's Konso region because it has a natural river within a 2-hour walk, allowing our water tower to have a reliable source of incoming water. This village has a population of around 2,000 villagers. Currently, the village does not have a water infrastructure, meaning that the women tend to be the ones to make the 2-hour trek every day to obtain water for their families. There are several factors that cause water depletion in this region. Ethiopia is currently experiencing more frequent and severe droughts than ever due to climate change directly depleting water sources. Another factor causing this water depletion is a rapid population growth, as their population has more than doubled since 1990. Additionally, many rural areas of Ethiopia lack proper water supply and sanitation systems, leaving the water contaminated due to poor sanitation practices, and industrial waste, which further reduces the availability of safe drinking water. The reason that we chose Taruba is that they are in dire need of access to clean drinking water. The village has a population of around 2,000 villagers, as I previously mentioned, and they face severe water accessibility challenges, with residents walking up to 2 hours to get water from seasonal rivers and ponds. The region does have some advantages compared to others, such as an established community water committee structure, strong local leadership, willingness for community participation, and more. However, due to the rural location of the village and seasonality of the water, sourcing water for our water tower will be challenging. But despite these challenges, we believe Taruba is the best candidate for our water tower. The successful design and implementation of our water tower relies on a strategic partnership with established nonprofit organizations that have proven track records in Ethiopian water infrastructure. The three nonprofit organizations that we chose to partner with for this project are Drop of Water, Water for Ethiopia, and People in Need. Together, these three organizations provide a partnership that combines technical expertise, community engagement, and local knowledge, all of which is essential to our project's success in providing sustainable, clean water access to the Taruba community. From an engineering perspective, the implementation of a truss water tower system in Taruba presents an infrastructure solution that addresses multiple socioeconomic challenges. Statistical analysis shows that women and children spend approximately 57 minutes per day on water collection tasks, resulting in an estimated annual loss of 347 productive hours per household. The structural design of the water tower would establish a centralized water distribution system capable of serving the community's baseline requirements. According to recent epidemiological studies, such infrastructure improvements typically reduce waterborne disease incidence by 45 to 60% in rural Ethiopian communities. This engineering solution aligns with Christian principles of stewardship and service, as the technical specifications directly address human suffering through sustainable development. Two Bible verses that emphasize the importance of helping others are Mark 12:31 and Matthew 25:35. Mark 12:31 states, "Love thy neighbor as yourself," and Matthew 25:35 states, "For I was hungry, and you gave me something to eat. I was thirsty, and you gave me something to drink. I was a stranger, and you invited me in." These verses show the importance of this project because they demonstrate faith through action and care and meeting a basic human need while affirming the dignity and worth of every individual created in the image of God.
The most important criteria if we're talking about designing is the required water capacity for a water tower, as this drives a lot of the dimensional aspects of our water tank and therefore our truss support. I read online with the Mayo Clinic that the recommended amount of water average between men and women is around 0.85 gallons per day per person. Thus, our village of approximately 2,000 villagers needs around 1,700 gallons a day. And to add on just a little overhead for population growth and whatnot, we are aiming to create a water tank that has around 2,100 gallons of water in capacity for our village. Our water tank design is going to be a cuboid design. This is mostly because it's easier to model, and also it makes it a lot easier for the construction process of our villagers, because we will most likely be using local populations labor. We're not sure how well educated they are in terms of construction, and we wanted to keep the design as simple as possible. And so we decided to go with a cube that is kind of a 5 by 4 feet by 5 by 4 feet, and then it's going to be 9.5 feet height, which is going to give us a volume of around 2,061 gallons of water, which meet our design requirements. It will also have a wall thickness of half an inch, also meeting our design requirements outlined. So our initial failed designs kind of failed for a couple of reasons. The one on the left failed because it was statically indeterminate. As you can see from the method of joint, kind of the diagram of joint A there's 3 unknown variables and there's only 2 known, so that's kind of impossible to solve. And then the one on the right failed because it's again a little too complicated with the angles on the truss supports. It is doable, but we kind of wanted to keep our design as simple as possible. That way we don't make any errors. These are our actual water tower designs with the given dimensions. As you can see, they're very similar. The one on the left and the one on the right are kind of very much the same. The one on the left just has a little more sections in it, and the one on the right has less sections. These are nice, kind of simple designs, very, very easy to construct, which again is important for our villagers' labor. The height and width is under the assignment descriptions for how tall and how wide our designs are allowed to be. And finally, we chose a height of 20 feet because it allows the water tower to produce a water pressure of 8.67 pounds per square inch of water pressure, which is a lot less than what we normally require in the United States standards for water pressure. However, because I'm assuming that the village doesn't have existing water pipes, we are figuring that the pump will be somewhere close by, so we won't really need as much water pressure because it won't have to go as far. Next, we're going to talk about input variables, which are going to be the wind force and also the weight of the tank and the water combined, which is what is being withstood by our truss designs. The wind force, we took a 12-month monthly average of the local wind speed, and we determined that it's around 7.22 miles per hour on average. Here's the formula we use to determine the force of the drag. It's 1/2 times the drag coefficient times rho times the surface area of the structure times our velocity squared. And here's kind of a little rundown of what those numbers are. We chose the coefficient of drag to be around 1.3 because NASA said that the drag coefficient for flat surfaces is around 1.3, and we only use flat surfaces on our design. And we're going to model the wind hitting it head on because that's when the drag coefficient would be heaviest. And then the surface area of the structures is just simply taking our truss design and then determining what the face of that would look like, and then adding all those together, as well as adding together the tank, the face of the tank. Here's kind of the Excel example for this calculation. It kind of breaks everything down, and then I have this, of course, for both design A and design B because design B needs to have a different amount of truss faces for it to work. We determined the weight of the tank and the tower using the following kind of Excel sheet. So we determined the weight of the capacity of the tank in gallons, and then we converted from gallons to pounds. And then we determined the weight of the tank by taking the volume of the outside of the cube and then subtracting the volume inside of the cube. That way we get the volume of the actual amount of material inside the cube. And then we multiplied that by the density of the material, which for our design, we decided to go with 1060 aluminum alloy, which I'll kind of talk about later. But yeah, that's kind of what we did. And then we added those two numbers together, and that was going to be our vertical component of our diagrams. Here's kind of just a summary of those variables across the different cases, which was important, obviously, because we were given different amounts of wind speed and capacity for our tanks to kind of showcase kind of the best case scenarios, the worst case scenarios, or just kind of like on average scenarios for our designs, which is very important as it kind of just showcases all the different outcomes for your designs. And here's the results of our simulations. The numbers are going to be in pounds. And again, I divided them out by case. So you can kind of see the negative numbers are going to be compressive forces, and the positive numbers are going to be tensile forces. Here's kind of the percent error of our hand calculations and our simulated values. As you can see, our percent error is very low. It's around 0% for both of our designs, kind of showcasing that our hand calculations are validated by our simulations. I decided to only showcase case 4 for the deflection, just because it's kind of our worst case scenario with double the average wind speed and 100% of water capacity. And quite frankly, a lot of the deflection diagrams look kind of similar, so I figured in order to kind of like save on time, I'd only showcase case 4, which is the worst one. But you can kind of see based off the coloring that design A has a lot more red in it, meaning that there's a lot more deflection movements kind of around that joint, whereas design B only has red kind of in that corner, kind of showing that it's handling the load a little bit better in terms of deflection. Here's our kind of key findings for our simulations. We determined that both design A and design B kind of performed very similar, meaning that design A doesn't really have an advantage over design B like we initially thought it would. Therefore, design B is a lot less truss members, so it would be a lot lower in cost because there's a lot less material there, obviously, which kind of led us to the decision to choose design B for our project. We decided to go with ASTM A572 steel because it's kind of the industry standard in construction and trusses, and it was easily sourced in Ethiopia. And then we also decided to go with 1060 aluminum alloy for our tank, as it is able to withstand the inside pressures of our water, and it's also a little cheaper, and it's also kind of lighter than other metal would be, kind of allowing us to have a little more leeway in our tensile strengths.